symmetric products.
Oh, thank you very much. Thank you for inviting me, for the opportunity to speak here, and to congratulate Michelle, even though belatedly. It's such a pleasure to be here in person after all we have been through. So my talk will be called Perverse Sheaves. Schobers on symmetric products. So it is based on joint work in progress with Vadim Schechtman. So I will start in the first part of the talk. I explain things that we understand well, and in the second part, maybe which we don't understand not as well. So let me start with reminding the context about symmetric products. Those are like very simple algebraic varieties. In fact, I will consider only the symmetric product of the complex line. Consider this algebraic variety, which is simply the quotient of Cn by Sn. It also can be seen as the space of effective divisors of degree m, something like this. Z equals sum multiplicities times Z, where coefficients are non-negative integers, and summing up. So of course, this space is known to be, so is the affine space. So it's the space of polynomials f of x equals xn, a1 xn minus 1 plus an. So as it is, it's identified with Cn again. But it has a natural stratification. So as an algebraic variety is very simple, but it has stratification. I call this stratification as 0. It's a stratification by multiplicities. So we consider multiplicities of such divisors. So strata correspond to partitions. Let me call them lambda. Lambda 1 greater than some lambda k, which is greater than 0. So, and the strata themselves, the closures of the strata are not smooth. So we consider the category of perverse sheaves with respect to the stratification pair of Sym and C. So it's a heart of the derived. I write a heart here. Sorry, so derived constructive category. Perverse sheaves. Perverse sheaves. Also, always with respect to middle perversity. So interesting. So the general sort of reason for considering perverse sheaves is that they are self-dual. So if you consider, say, cohomology and homology, then intersection homology is in the middle. And similarly, this corresponds to the corresponding data. So for cohomology, we have sheaves. We have cohomology with coefficients and sheaves. So here is this something which can be called co-sheaves. And so perverse things are in the middle. There's interesting category, and So this category is identified, just to simplify it, with perverse sheaves of decant quotient by shifts, by translations. So there is action of additive group here, simultaneous translation. And then, for example, for n equals 2, we get, after the quotient, we get just complex line with 1 point. So it's the same as category of perverse sheaves on C with singularity on 0. For n equals 3, it would be third symmetric product, but we quotient by the shift, we get C2. And the strata would consist of this semi-cubic parabola, or rather this open part, and the cusp point. So it's the same as perverse sheaves on C2 with respect to semi-cubic parabola. Y square equals x cubed. So what I will do, I will recall a description given with Vadim on this sheaf. So I recall features. Now, before I do this, I just mentioned that there can be two generalizations, which I won't go into, but which are also interesting. So one generalization, instead of this, we can consider the quotient of a Cartan subalgebra by the Weyl group of a reductive Lie algebra. And the other would be that divisors with coefficients. So here I write in Z plus, but in some monoid, in more general monoid L. And this includes the run spaces. But I will focus on this simplest example because it's very kind of easier to explain what is going on. So now I have to erase something. Let me see how can I do this. So the main feature I want to recall is the concept of what we call contingency matrices. I start with partitions, but not like this. So here partition is unordered, even though I have inequalities here. The meaning of this, it's the decomposition of a number into sum of the lambda i's modulo permutations, and we order them just to fix this. I consider the set OP of n set of ordered partitions. So it's a set of just vectors, alpha 1, alpha k, alpha I in Z plus, and sum alpha I equals n. So, and let me denote by CMN what we call the set of continuous matrices. Sorry, contingency matrices. of content M. That simply means a matrix. Move it higher. Simply means a matrix M, which is M11, M1L, MK1, MKL. With the following property that Mij are non-negative integers, and no rows and columns which are entirely zero. No zero rows or columns. And sum of Mij, the content means that the sum of Mij, or all I and j, equals n. But instead of summing all of them, I can sum them in rows and get a number for each row. And I can sum them in columns and get a number for each column. So here I can write alpha 1 is the sum, would be sum M1j. You have alpha k equals sum mkj. And here I can do beta 1 is this sum beta L. So I associate to such a matrix two ordered partitions. So here I should say this, it's also not equal 0. I write strictly positive. That's why I get two ordered partitions, which are known as the margins of this matrix. I can say alpha equals alpha 1, alpha k, and beta equals beta 1, beta L. We call this horizontal margin. This we call vertical margin. So there are ordered partitions of them. So then this set of matrices is decomposed by the data of horizontal and vertical margins. Cmn is simply disjoint union over alpha and beta in ordered partitions. Let me call it Cm of alpha beta. So this means with these margins. So in remarkable, this concept has several appearances in mathematics, which are not all exactly identical. And I list those appearances. Sort of the original appearance is where we got our terminology is from statistics. So a matrix M gives, it corresponds just to a joint distribution of two random variables with those, if you normalize this to 1, if you divide by n, and normalize this to 1, divide by n, we get two probability distributions. And this is like joint distribution of two random variables with those distributions. You call it like this, joint distribution. In a sample. For example, we want to study correlation between smoking and death. We can write here the number of cigarettes a person smokes every day, and here like the age of death And in a sample of large number of people, we get some information. For example, if this matrix is of rank 1, it means that the two random variables are independent. If there's not rank 1, then there is dependence, there is correlation. So let me write it like this. Rank. I'm sort of close to 1. I just write approximately equal to 1. It means that M is close to matrix of rank 1. That means independent. This one distribution, this won't really play a role. It's just to explain the terminology. So I put 0 there. So the other appearance is that we have a natural cell decomposition. I call it S2 of the symmetric product. So there was S1, S0 was stratification, a complex stratification by multiplicities. There is S2, in fact, it's convenient to do this because technically there is one intermediate in between them, but I won't talk about it. So the composition goes like this. Suppose we have a divisor, Z, sum and Z times Z. So lies here. Then just look in the in the complex plane. It's a complex plane, which is simply R2 and has the X coordinate and the Y coordinate. So we have some points here. So let's look at what are possible X coordinates of this point, those points. Maybe some points have the same X coordinates. Maybe some of them don't. We do it like this, and call them, say, X1, Xk. Those, so X1, Xk, possible. So Z equals X plus Iy, possible array of Z. So for which NZ is non-zero. And here we also do so. Say this is Y1, this is Y2, this would be YL. So Y1, that's YL. Same for imaginary parts. Once we do this, then our points, all the points of our divisors are on a grid. So we get a matrix, K by L matrix, by just looking at the multiplicity of the point in position K plus L, KL. We write M mu nu of Z equals the multiplicity at the point X mu plus Y nu. It's multiplicity. So we get a matrix M of Z, which is M mu nu of Z. It says contingency matrix because we number things in such a way that there is no zero, we don't get any zero row or columns. And we consider UM to be the set of all Z for which M of Z equals M. And this, in fact, is a cell. If you think about it, so if you prescribe the multiplicities and just move those things, stretch them around, then there is, it's a cell. So because those become the parameterizations of the cell of dimension K plus L. So, and this we get stratification S2, and it refines stratification by total multiplicities. We can say that S2 refines S0. So in particular, any constructible sheaf or complex with respect to this stratification is constructible cellular, we can say, with respect to this cell decomposition. We can analyze it combinatorially. Say it again. Yes, they're real. They're not complex at all. Yeah, cell of all dimensions. Yes. It's related. It's also refines the so-called Fox-Neuvert stratification, which was also considered by Fuchs. So we use terminology by Dimitri Fuchs. So we use terminology Fox-Neuvert-Fuchs. So that's one natural appearance, which it's relatively new, which means we stumbled upon it. But there are some other appearances which are more classical, and it's comparison of those which makes things interesting. So one, well, appearance number 2 is the formulas in Hopf algebras. Formulas and Z plus graded Hopf algebra. So we have such an algebra A, which is direct sum for n greater than 0, an. Suppose the 0 part is our base field. And we have 2 such partitions, so alpha and beta are ordered partitions. Then we can start with the product A alpha, which is A alpha 1 transverse 1 transverse A alpha k, and then multiply them mu into an. Mu is the multiplication. And then co-multiply them back by delta into another things like that. A beta 1 transverse A beta. So the compositions is equal. Composition. I mean, this map equals. Let me write it in a. I probably do have space to write this. Equals to sum over matrices, over contingency matrices in Cm of alpha beta. And we can do like this. I write this vertically. A alpha 1 times A. Oh, no, sorry, what I'm doing. That's it. Catches up. I write it vertically. A alpha 1 times A alpha k. And each of them I can co-multiply. So I do this by delta into A M11 times A M1L. And this, so each of them I co-multiply along the rows of matrix. Delta A MK1 for A MKL. So, and so I get like a 2-dimensional array, or tensor product of a 2-dimensional array of matrices. And then I can multiply by mu into A beta 1 A beta by mu. So that's completely elementary treatment, elementary statement. So the case K, if the case K equals L equals 2 is the basic thing, which if we write compatibility of multiplication, co-multiplication in terms of graded component. So everything else follows from this by induction. And then the third appearance, where am I? Okay. Third appearance is the parabolic Bruhat decomposition for GLN. Suppose alpha again is as before. Then we have the corresponding parabolic subgroup P of alpha equals, well, GL alpha 1, GL alpha K. So if I write double quotient GLN by P beta by P alpha equals Cm alpha beta. So this is space of relative position of two flags, two filtrations, two flags, or two filtrations. So I can say in Cn I have one filtration is F1 Fk equals Cn, and the other would be, say, V1 VL equals Cn. The two, we have two flags. Then what are invariants? We can take the second graded. So it's a known lemma that gr I f gr j v Cn is identified to with gr j v gr I f Cn. Sometimes called Sassenhaus lemma or lemma on two filtrations. This holds in any abelian category. Dim equals Mij. Now, for example, if all the margins are identically one, then M is a permutation matrix. So we get the symmetric group. If both margins are just rows of ones, then we get the symmetric group. Where am I? Oh, okay. Now, a little bit alternatively, I can say that we can also take symmetric group. And here we have S alpha and S beta. When S alpha is a product of S alpha 1, S alpha k. And this is S beta 1, S beta L. So it is the same. The essence of Bruhat decomposition is the quotient of the group. Reductive group is the same as quotient of the corresponding symmetric group. Now, if you look at this, and this is more this part, in some sense, they are not far removed. It's purely algebraic manipulation with the indices. And if you look at what's involved in those manipulation of the indices, it's something like this. So this is not so surprising, this match. But the match with this is a little unusual, because it's a different thing. It's a geometry of the space of the symmetric product. So now let me discuss how to pass from that self-decomposition to a description of perverse sheaves. Let me call this third part here. I'll continue here. So I'll call it Janus sheaves. And perf, Symn and C. we want to extract a description in terms of certain combinatorial data labeled by such matrices. And we experimented with different names, but probably the name of Janus sheaves, which is kind of borrowed from I think the first person who was used some kind of data like this called Janus functors was Teimuras Perashvili. So we owe him the terminology. Perashvili. In a slightly different, but in fact related concepts. So, but it's a convenient because Janus is supposed to have one face looking forward and another face looking backward, right? So we have this cell decomposition. We want to describe sheaves in a cellular way. So let's look at the PO set as a partial ordered set of cells. So with respect to obvious relation of inclusion of closures. So what is this PO set? Is this set of continuous contingency matrices with some order? So let's find out what is this order. So first of all, I should say that this type of cell decomposition is what is called regular or quasi-regular. It means that two cells cannot come together to a smaller cell from two sides. So we have no such. So if you want to describe cellular sheaves on something like this, we cannot use the PO set. It is covered by Macpherson's concept of the category of exit paths. But in this, it is not needed. We just use the partial order. To say more precisely, the category of exit paths is identified with the category corresponding to this PO set. So let's look at this PO set. Actually, I raised the geometric picture, but if sort of we still imagine it here, that this PO set, this partial order, splits, or in fact is generated by two partial orders. The horizontal one, I write with prime, and vertical one, I write it with second. So it simply means that if you have a matrix, then I can sum some adjacent rows of adjacent rows of the matrix, or I can sum some adjacent columns. How? This is not visible, but how can? Suppose this is my divisor. How it can degenerate into something smaller, the closure of the cell. Well, we can first collapse them like this, or we can collapse them like this. And if you think there is no other possibility, everything is decomposed. Every way of degenerating is decomposed into horizontal collapse, followed by vertical collapse. So if I have a matrix M, so it's greater in the first sense. So it's obtained by summing some groups of adjacent columns. And in another sense, the same for rows. For example, I have 1, 2, 3, 4, 5, 6. This is a matrix. I can sum this column and this column. So I get greater in the first sense, I get 3, 9, 6. Or I can sum this row and this row, and I get 5, 7, 9. So, as I said, since there are no such things, then the category of constructible sheaves is simply the category of representations of this poset. It's a general principle of constructible sheaves that they have generalization maps. So if I have something on the smaller stratum, so suppose my sheaf is locally constant on this strat, then the space of the stock here is the space of sections on the small neighborhood. And the space of sections of the small neighborhood maps to stock here, which is the same as stock here. So I have so-called generalization map. And it is covariant from smaller strata to larger strata. Even though for a sheaf, the restriction is covariant, usually sheaf on the level of open sets is a contravariant data from something bigger to something smaller. But on the level of stocks, it's the other way around. So I have the category of constructible sheaves of Sym and C. It's simply the category of functors or representations from CMN. This is the category of vector spaces. So M, every matrix M, I would associate a vector space G of M. Yep. And since the order is generated by the two of them, I can say that whenever I have include inequality in the first sense, I have G of N goes to G of N. And if I have an inequality in the second sense, also I get G of M, G of M. So they will be transitive and will commute. Transitive. And so they're both covariant, both go in the same direction. And if now I want to consider the complex stratification, sheaves S, 0 is same, plus those inequalities which lie in the same stratum go to isomorphisms, and let's call them anodyne. Again, just the anodyne inequality. Isomorph. And what does it mean anodyne? Which means in the same as zero stratum. What does it mean? That such inequalities in which the multiplicities unchanged. Multiplicities. And what does this mean? It means that we sum things along the rows and columns, but really the numbers, the non-zero numbers don't change. So I'll just give an example, it will be clear what I'm talking about. For example, I have 1, 0, 3, 0, 2, 4. Right? And I sum those two rows, I get 1, 2, 3, 4. It's an equality which is anodyne. I write ANO. Or I have 1, 0, 2, 0, 3, 0. And I sum those together, I get 1, 3, 2. I get an equality which is anodyne. So we can describe constructible sheaves in this sense. Also can describe constructible complexes too, because complexes would be just representations of such things into complexes. Okay, so now maybe I'll use the other boards. Now let me give a definition. A Janus sheaf on Cmn is a datum. It's very much like this, but I want it to be covariant in other direction and contravariant in the other direction. So first of all, for every m, we have a vector space, E of m. So then when n is less or equal than m in the first sense, then I have maps called del prime nm from En to En. Will be transitive and also satisfy the anodyne condition. And when n is less or equal than m in the second sense, and I have the del second mn in the opposite direction, em to en. Again, similar properties. So, but before we said that the two such things commute. So here the commutativity is slightly more involved. Suppose we have the situation, we have a matrix M, which is less or equal in the first sense to N, and in the in the other sense to P. Then we can compose, want to say how, suppose I write delta prime Mn, so del second Pm. So it's going to be not, so here it will be just a commutative diagram. Here will be a version, I write the sum over, here, let's write M, less or equal prime N, less or equal second P, and will be some Q here, which sort of fit into, let's call it a Cartesian diagram or something like this. And here I write in the opposite way, del second Qn, del prime PQ. So notation for this, so it's not to write this much. Later I say notation. Q lies in the supremum, kind of mixed supremum of P and N. So again, it's natural way of commuting, except now they go into opposite directions. Now, our theorem is that Sym and C is identified with the category of such Janus sheaves. So a perverse sheaf F is a complex would correspond to data called EF. But now let me explain. So, and this is something that took us some time to realize as clearly as we realize it now. So such a perverse sheaf is a constructible complex. So in particular, so F is lies in the derived category of is S2. It's a constructible complex with respect to the cell decomposition. And by the previous discussion, by this discussion, so this was discussion for individual sheaves, but there is a similar discussion for complexes. And objects of derived category would be represented by a complex of such things which commute. So therefore we give, say, G dot F is a representation of Cm with two partial orders select. So it's a cellular complex. Just representation of that doubly ordered set. Now this thing is nothing but relative Verdier dual. So let me explain what it is. Relative relative, and here I write cell relative means with respect to the second order, relative cellular. So what do I mean is that Verdier duality, if you want to do it without dualization, it is between sheaves and co-sheaves. Verdier duality without dualization is between a certain just manipulation with cellular data. If you do this, we start with the covariant cellular data, we get contravariant cellular data. And if you want, we can dualize, and that will be the Verdier dual complex. But if you don't, and stop here, it will be a co-sheaf. So if you do this in one with respect to one order, so we get a mixed thing, and it would satisfy those conditions, more or less tautologically. And the important kind of interesting phenomenon is that the T structure, the perverse T structure here, is being sent to the ordinary T structure here. So it is not a complex. Here it lies in vector spaces, not complex. Not a complex. Every datum would be a priori will be a complex, but what condition to? Actually, I don't have that much time. Oh. Let me try to. Let me give you one example how it matches the concept of a Hopf algebra. So it was A equals direct sum, and AN is a graded Hopf algebra as before. Let's for every n consider EA and it sends every matrix M into let me call it A sub M, which is simply the product of all ij A Mij. So with something like A M11 under A M1L, tensor A MK1, tensor A MKL. So now when we have the matrices collapse in horizontal and vertical sense, then we can use either multiplication and or co-multiplication. If m less than n in the first sense, horizontal, we have A m to A n with co-multiplication in the rows. And when m is less than in the second sense, we had A n to A m multiplication. So, and because the properties of, say, the two appearances of contingency matrices, one is formulas for manipulating Hopf algebras, and the other is cell decomposition. That this is a good Janus sheaf. So this gives a perverse sheaf. So therefore, F dot AM and in fact, in this way, we get factorizing systems of perverse sheaves because for different n, we have factorization property. I won't go into this. For different. Well, I'm very close to the time. So let me just say what somehow is the project we are working on. So from this, from this, we want to categorify this. To get the definition of perverse schobers, categorical data. On Symn and C. So in some sense, the definition sort of suggests itself. We should have such a data, E consisting of E of M triangulated categories, or in fact, enhanced in appropriate sense, enhanced, DG enhanced or stable infinity enhanced. We have the data D prime, D second are exact functors. Now this condition, sum would replace by some natural filtration, which is a part of a data. We have to explain what does it mean, a filtration in triangulated categories, some kind of Waldhausen data, the data of the Waldhausen construction. And when I say filtration, so here I sum over this set of supremum, but this set of supremum has a natural Bruhat order. Because, say, the set of CMN, Cm of alpha beta equals GLN by P alpha by P beta, certain orbits, they have natural order. And the other thing is sort of version is a product of such thing, the natural order. So if a good example when we have this is the category of representations of general linear groups over finite or p-adic fields, when the formulas in the classical theory of Bernstein and Zelevinsky give such filtration with induction and restriction. And it appears in probably in many features of representation theory. So this is somehow what we are working on. We haven't fixed all the details, but somehow this seems to be the natural direction. Thank you very much.